All right, welcome to part 3 of the statistics review. In this video, I'll be talking about probability, some basic rules and concepts with that, also principles of counting, which will play into probability. I'll discuss Bayes' rule, and then also the concept of expected value and variance. So probability, we're looking at here a numerical measure of the likelihood that an event occurs. So probability is going to be a number. It's going to range from 0 to 1. Values near 0 indicate that an event is unlikely to occur. And if it's near to 1, it indicates that the event is almost certain to occur. So here we have statistical experiments, and probability determines outcomes. So we might have an experiment that's repeated in exactly the same way, but entirely different outcomes can occur. So an example might be a customer comes into a store. Sometimes they might buy something, but other customers, or on other occasions, the customer doesn't buy anything. So we repeat the experiment, somebody coming into the store, but we get different outcomes potentially. So for this reason, statistical experiments are sometimes called random experiments. Now, as part of thinking about how likely something is to occur, we might want to think about how many different things could occur. So in the previous example, the customer either buys or doesn't buy, but we could think of more potential outcomes, such as they make $1 worth of purchase, or they make $2 worth of purchase, or they make $2.51 worth of purchases. So in that case, there would be lots of different possible outcomes. So here we're going to think about counting rules for combinations. So the number of combinations of n objects taken k at a time, n and k are numbers. And so a useful counting rule enables us to count the number of experimental outcomes when k objects are selected from a set of n objects. And here is one notation for that. You see, there are other possible notations. So here it's n choose k is what this says here. This thing is read n choose k. But some places you might see it as n choose r, or big N choose little n, or something like that. So the notation can vary. But here's the formula. Most likely you'll have access to a calculator in most situations, or something like Excel, depending on the setting, and you'll be able to punch that in and get an answer out, as opposed to using this kind of formula where n factorial, this n with the exclamation mark is read n factorial, means what you see here. So in many situations, for example, you're taking a test, you might be using a calculator to get this out. Now, an example of this would be, and here I invite you to pause the video at some point and check this using your handheld calculator, or if this isn't for an exam purpose, you want to double check with something like Excel. But you can pause the video to just check that you can get the same number. So let's suppose a company has 4 openings for manager positions. There are 11 people in the company that qualify for those positions. What is the number of current employee combinations possible for filling the 4 openings? So how many different possibilities are there? So we just plug that in, right? We have 11 choose 4, and we get 330 out. The probability here of thinking about any specific set of 4 employees. So pick 4 people out of those 11. What's the probability that those 4 people, that specific group, will get the promotions to manager positions? So it's 1. That's one possible outcome out of 330 total, and that gives us a probability. So here, somewhat small. So that is how we might calculate or figure a probability in this setting, and why we might use a kind of counting rule for getting this. Another example is that of a lottery. So in January of 2016, the Powerball lottery reached over $1 billion. It's actually done that more than once. Let's suppose we have a lottery and it has 40 numbers to pick from, and you can pick 5. So how many combinations are possible? And then what is the probability of picking the winning combination with one ticket? So again, you can potentially pause this, see about getting the answers before I show them in just a moment, or you can just follow along. So how many combinations are possible? We have 40, choose 5, and the answer comes out, you can double check this on your calculator, 658,008. And then we think about what's the probability of winning. Well, if you just bought one ticket, you'd have one here out of the 658,008, and you get a very small or low probability. If instead you were able to buy 2 tickets, then you would have double this, 2 out of 658,008, and this number would be doubled. But with just one ticket, it's just 1 out of that number of combinations. Now, thinking about probabilities again and assigning probabilities to a particular outcome, such as you win the lottery. So the value that's assigned to the experimental outcome has to be between 0 and 1. So in this notation here, the E sub I is the ith experimental outcome, and P of E sub I is its probability. So this probability has to follow this rule that it's got to be less than 1, or it could be equal to 1, and greater than 0, or could be equal to 0, but it has to be in between there. And then if we were to add up all of the different possible events, so you've got more than one E sub I, then add those all up and they're going to reach 1. So in the very simple example a few minutes ago of a customer comes into a store and buys or doesn't buy, those two potential values, you would have one of the E's, the events would be buys, and one of the E's or events would be doesn't buy. Add them up and it's going to be 1. Now with probabilities we can have the complement of an event, and that's just all of the sample points that are not in the event A. So we might denote it with a C in the up in the corner or superscript there. There are other ways of denoting it depending on maybe what textbook you might be looking in or who's writing it, but this is one way of writing it out. Note that the probability of A and the probability of the complement of A will equal 1 because we've accounted then for all possible events. So an example could be event A is that a person is employed, the complement is that they're not employed. We have an addition law, and that provides a way of computing the probability of event A or B or both A and B occurring if we know certain parts. So to write out this law, it's the probability of A union B. So this symbol here is red union, and that's the probability of A plus the probability of B minus the probability of the intersection of A and B. So this symbol here is red intersection. So we could get the probability of A union B happening if we knew the probability of A, probability of B, and the probability of their intersection, right? So this part here is the probability that either happen, and this over here, the probability of A intersect B, is the probability that they both happen. But we can use this formula in certain settings to make calculations. The union of events A and B is the event containing all sample points that are in A or B or both. So the union of events A and B is denoted with the symbol that we saw on the previous page or image. The intersection of events A and B is the set of all sample points that are in both A and B. And the intersection of events A and B is denoted with the symbol that we again saw just a minute ago. All right. Two events are mutually exclusive if, when one event occurs, the other cannot occur. So if events A and B are mutually exclusive, the intersection of the two events is 0, or I should say the probability of the intersection of the two events is 0. Conditional probability, the probability of an event given that another event has occurred, this is what we call conditional probability. So the conditional probability of A given B, the way that we write that is with this expression here. So the way that I read this is the probability of A given B. How do we compute that? Well, when we're computing the probability of A given B, so this expression here, what do we have in the numerator? In the numerator we have the probability of A intersect B, so this is the probability that they both occur, sometimes called the joint probability, and it's divided by the probability of B, which we sometimes would call the marginal probability. So that's the expression. So in this case, of course, it's assuming that we have access to, or we know what the probability of B is, and that we know what the probability of the intersection of A and B is. So otherwise, of course, we can't make this calculation. All right, so now we want to consider an example, or a couple of examples, of finding a conditional probability. So we want to take the probability of no purchase given that the person has a coupon. We're going to use these data here in this table to make this calculation. So no purchase, look at this part here, and coupon, so coupon here, we would be getting the intersection. So this, the formula again would have had us look at the probability of A intersect B, and we can consider these things to be A and B. So what we've got then here in looking at that is we have the intersection is this part that gives us the 8 here. This was the intersection. That's what's coming up right here. And then the 77 is coming from adding the 8 plus the 27 plus the 42. Adding those up give us the 77 that we see there, and then we can punch that in a calculator to get us out this value here. Then the second example asks us to consider the probability of no coupon given a purchase of at least $50. So we can look at the intersection, so no coupon, looking at this, and purchase of more than $50 is this. So what is the intersection there? The intersection there is this 32. And that 32 is what I'm placing up here. And then out of B, so A given B, the B part would be purchase greater than $50. We're looking at now 42 plus 32, that's 74, and that's where this 74 here comes into play. And punching that in on a handheld calculator, for example, you can get 0.432432 and then more decimal places if you want. So there's a couple of examples of finding a conditional probability from a small set of data. Now there's something called the multiplication law. You see that here. So it provides a way to compute the probability of the intersection of two events. So this is just a rearrangement of the formula that you saw a few minutes ago for the conditional probability. So the probability of the intersection of A and B can be rewritten as the probability of B times the probability of A given B. So as an example, let's suppose the probability of B is 0.4, the probability of A given B is 0.6, then the probability of the intersection, probability of A intersect B, is just going to be 0.24, which is just 0.4 times 0.6. Independent events. If the probability of A is not changed by the occurrence of event B, then the events A and B are independent. So two events A and B are independent if the probability of A given B is the same as the probability of A, right? So the probability of A is not changed by knowing that event B happened, and the probability of event B given A equals the probability of B. So the same thing, we can look at it either way. Bayes' theorem. Sometimes this is referred to as a situation where we're looking for a posterior probability. But sometimes we might think of it as a conditional probability. So to find the posterior probability that event A sub I will occur, given that event B has occurred, we're going to use Bayes' theorem in this setup here. So what you have in this formula that looks somewhat long is you've got the probability of A sub I given B. Over here, this is what we're solving for. And with A sub I, thinking of A sub I, there are various events A that could take place. So you've got A sub 1, A sub 2, it could be A sub 3, A sub 4, all the way out to A sub n, right? So it's fairly general. I'll show an example shortly where there will be A sub 1 and A sub 2. But the way that this is going to be written here is you have the probability of A sub I, so the event of interest. So this could be something that happens, of course. So maybe this is that a particular stock rises in value by a certain amount. So that could be A sub I. The other A's is that the stock rises in price by less than that, or that the price of the stock stays unchanged, or that the price goes down, right? Those could be some of the different possible events here. And then B, that we would have, the conditioning event, maybe is that some other announcement was made. So for example, the Federal Reserve Bank announces something regarding interest rates, that they're going to lower interest rates or raise interest rates. Or it could be that a company announced a merger in a related industry, or that two competitors announced a merger. Whatever it is that B might potentially be, whatever that event is. So we're looking at the probability that the event of interest takes place, but then over here we're looking at the probability of that conditioning event happening given our event of interest, A sub I, taking place. So that might not seem intuitively the way to think about it, but this is what this Bayes' theorem tells us. Then in the denominator, we're going to have that specific A sub I will be part of one of these, right? It will be one of these probability of A1, 2. We don't, in this general formulation, we don't specify what I is, but it would be 1 or 2 or 3 all the way out to n, be one of those. And so then this is formulated, just look at this first part here, because it's going to be repeated for A sub 2, 3, all the way out to n, is just take the probability of A sub 1 times the probability of B given A sub 1. So again, might not strike you as immediately intuitive, but this is what Bayes' theorem states. So Bayes' theorem applies when the events for which we want to compute posterior probabilities, so that's the A sub I, are mutually exclusive. So A sub 1, A sub 2, A sub 3, for example, are mutually exclusive, and their union is the entire sample space. So one of them is going to occur. All right. So now, let me give you an example here. A manufacturing firm receives shipments of parts from two different suppliers. The quality of purchased parts varies with the source of supply. So maybe they have a high quality supplier and a low quality supplier. It buys 65% of its parts from supplier 1 and 35% from supplier 2. So you see the notation there. P of S sub 1 is 0.65 and P of S sub 2, so the probability of coming from supplier 2 is 0.35. So historically, 98% of supplier 1's parts are good and 2% are bad. and 95% of supplier 2's parts are good, while 5% are defective. So supplier 1 might be the high quality supplier, supplier 2 is the lower quality supplier. So with these numbers, and you might want to copy them down if you want to review this example, or you can pause and go back and forth, but you might copy these values down. What we're going to have here is, if I want the probability that a part comes from supplier 1, given that it's defective, so this is a kind of forensic operation here. You observe that it's defective, you're wanting to estimate or find the probability that it came from supplier 1, you're going to plug in the values that you had given just a minute ago. So if you need to rewind or if you wrote them down, either way, those will be plugged in the fashion that you saw just a moment ago, right? So in this case, you're thinking of this would be something like A sub I, or in this case, right, we could write it down as 1, and then this here is B that is defective. So in this scenario here, though the 0.35, that would be the probability that it came from supplier 2, so we could write this maybe as A sub 2. This pen's not showing up super well, but A sub 2, right? And we might think of it that way, right? So then you get this value out here. Go ahead and pause it and check the math. Then take a minute here, go back to find the values, and go ahead and pause the video if that helps you, and find the probability that it came from supplier 2 given that it's good. So give you just a moment here to go ahead and pause the video and then work that through if you're interested before I show you the answer here in just a few seconds. All right, so hopefully what you found, if you're plugging the values back in for the probability that it came from supplier 2, given that the part is good, is you plugged in the values that you see there, and you got 0.34296. So where do some of these things come from? Let me illustrate a little bit in this here, is that, again, this 0.35 is, you're thinking of this S sub 2 now, maybe that could be A sub 2, for example. And this good is the event B here. So this probability here then, the 0.65, would be that it came from supplier 1, right? It's A sub 1 using our notation before. I'm having a little problem with the pen. There we go. That would be A sub 1, right? And then this right here, right, is the probability. My pen's giving me some problems here. Probability B, which means good, given that it came from supplier 1, which my pen is giving me some little fits here, but we'll go with that. So hopefully, though, you were able to find this value. If not, double check your values. You can go back and look at the example or look at the values a couple of slides back. All right, the concept of expected value, or the mean. So if we have a random variable, this is a measure of its central location, a concept previously covered. We often use the Greek letter mu to denote the mean. And here, for a discrete case, we use the summation of all of the particular values or possible outcomes. These are the x sub i's, times their probabilities. This what I'm denoting here with the f of x. So it's just a weighted average of the values that the random variable may assume. Those are these x sub i's. And the weights are the probabilities, which are represented by the f of x. So I've got that here, the f of x. And so the expected value does not have to be a value the random variable can assume. So for example, you could be looking at the different number of children that a family might have, and the potential values are 0, 1, 2, 3, and so on. But the average might be 2.6 or 1.7 or whatever it might be in a particular area. So it doesn't have to be one of the values that were initially available, 0, 1, 2, 3. It could be 2 point something or 1 point something in that example. So we have that for expected value, and then we have for a measure of variability or dispersion, we have the variance, and that summarizes the variability in the values of a random variable. And you see the formula here. So again, it has this difference between the random variable's value and the mean, and then it has a probability here again as well, just as you saw in the previous example. So if you think of the empirical variance, and that would be a case where you've got some data that you might be looking at. What did you have here? You had a formula that looked something like this. You summed up the x values, and sorry, my pen is not wanting to cooperate with me. There, instead of mu, you would have had x bar, the sample mean, and you would have performed the same function. Sorry. And squared it. Sorry, this isn't. And instead of multiplying by probability, we would have assumed that everything was the same probability, hence dividing it by n minus 1. Okay, so pen not being very helpful for me right there. All right, so the variance then is a weighted average of the squared deviations of random variable from its means, and again the probabilities are those weights. The standard deviation then, sigma, is the square root of the variance. So here's an example of computing the expected value. You just take this table. Let's suppose it's the number of gallons of milk that might be bought in a store visit. The possible values are 0 through 5. The column f of x gives us the probability, and then the column x times f of x is just the product of the two, x times f of x, and then there at the bottom where it says total, we've summed those up. So if we're adding them all up, we get 0.9. So the expected number of gallons of milk that we purchased would be 0.9. If we're looking at the variance then, we're going to get a value of 1.394, and then the standard deviation is just the square root of that, 1.1807 gallons. Now the table here is constructed so that, again, we have all the values of x, 0 through 5 gallons of milk. We look at the difference between x and mu. So in the first case, 0 minus 0.9 gives us negative 0.9, and then 1 minus 0.9 gives us 0.1, and then so on down the rows. Then in the next column over, x minus mu squared, just taking that value and squaring it. So the negative 0.9 squared gives us 0.81, which we see right here. And then so on down, so that if we take 4.1 and square it, we get the 16.81, all the way down. All right, do this for each potential outcome. And then to get this last column here, we're going to multiply this gap, right? So this difference squared, the 0.81, times the probability, the 0.38. So that's what you see here to get out this value. And this is done for each row. So do it here, do it here, it's done here, and so on, until the bottom we get the 1.394 by just adding all these up, right? So we just add these up to get to the 1.394, which is the variance, and then take the square root of that to get the standard deviation.